So good afternoon and good morning, everyone, depending on where you are in our virtually connected world. I'd like to thank the organizers for giving me an opportunity to tell you about the Origin Space Telescope. I'm giving this presentation on behalf of hundreds of scientists around the world and engineers concentrated at NASA's Goddard Space Flight Center who participated in a 3.5-year-long mission concept study. NASA has a proud history of implementing the missions recommended by the Decadal Survey, which is conducted every 10 years by the U.S. National Academies of Science, Engineering, and Medicine. The previous decadal missions were Hubble, Chandra, and Spitzer. The James Webb Space Telescope will launch in about a year, and the Roman Space Telescope, previously called WFIRST, is in development. The 2020 Decadal Survey is underway now and considering 4 large telescopes. We don't yet know which one of these telescopes will become NASA's next great observatory, but it's possible that it will become the Origin Space Telescope. The Origin Space Telescope is the only one of these new mission concepts that would operate in the far infrared. Origins will offer 1,000 times greater sensitivity than any previous far infrared telescope. It was designed to address 3 compelling science goals and will be used by the community to make new discoveries that we can't even imagine now. It will operate in the wavelength range from 2.8 to 588 microns. As I mentioned, 3 science goals served as mission design drivers. The goals are to answer these three questions. First, how do galaxies form stars, make metals, and grow their central supermassive black holes from the epoch of reionization to today? Second, how do the conditions for habitability develop during the process of planet formation? And third, do planets orbiting K and M dwarf stars support life? Corresponding to each of these goals are 3 scientific objectives. Specific measurements are required to address the objectives, and certain capabilities are necessary to make the measurements. All of this is summarized in a detailed science traceability matrix, which can be found in the final Origins Concept Study Report. Briefly, the required capabilities are exquisitely sensitive spectroscopy in the far infrared, combined with the ability to map a large area of the sky quickly, sufficiently high spectral resolving power to detect and resolve water and deuterated hydrogen spectral lines, and superlative stability to enable spectroscopic measurements of transiting exoplanets and detect biosignatures in their atmospheres. The Herschel Space Observatory provided wonderful surveys of the sky in the far infrared, but had relatively modest sensitivity and resolution. The Origin Survey Spectrometer, the Origin Survey Spectrometer, one of 3 Origins instruments, will allow us to study these galaxies in detail out to high redshifts. The spectral lines accessible to Origins will distinguish galaxies dominated by their central nuclear activity, active galactic nuclei, or AGN, galaxies dominated by star formation activity, and galaxies in which feedback is an important process on scales from parsecs to megaparsecs. Here you can see the 3 different, I hope you can see my cursor, you can see the 3 different types of astrophysical processes. They light up each different spectral lines. At redshift of 0, you can see the Circinus galaxy spectrum, and as you look farther out into the universe at higher and higher redshifts, those spectral lines move into the far infrared where they're accessible by Origins. To learn how the conditions for habitability develop during the process of planet formation, Origins will measure water vapor and ice in protostars and protoplanetary disks. Measure the total gas contents of these disks using the reliable HD molecule as a tracer, and look for a connection between comets and Earth's oceans as indicated by the ratio of deuterium to hydrogen. The spectral lines of water molecules are accessible to the James Webb Space Telescope and Origin's spectral ranges, and a few lines are detectable in atmospheric windows available from the ground with ALMA. However, many of these lines are only excited in shocks or at high temperatures, whereas the water in planet-forming disks is quiescent and cold and accessible only to Origins. Origins will detect the rotational spectrum of water at temperatures below 1,000 Kelvin above ground state in more than 1,000 planet-forming disks to help us understand how habitable worlds form. Comets that match the Earth's oceans in their D to H ratio are rare, but Origins will be able to measure the HDO to water line ratio in over 200 comets and asteroids to understand the role these objects played in delivering water to our own inhabited planet. For its third main goal, Origins will be used to search for biosignatures in the atmospheres of exoplanets. Specifically, Origins will measure the 2.8 to 20 micron spectra of exoplanets orbiting late-type K and M dwarf stars. These are the most common stars in the universe, but they may not be hospitable to life as we know it. Nevertheless, we will only know if we look, and Origins can actually find signs of life. A biosignature is a combination of molecules like methane and ozone that chemically self-destruct and probably require a biological process to sustain. Origins will observe enough planets to know if life is common or rare on planets hosted by K and M stars. The Origins Space Telescope has 3 science-optimized instruments. The Origins Survey Spectrometer, or OSS, has a low-resolution mode for spectral surveys and a high-resolution mode over the entire far-infrared region, from 25 to 588 microns. There is also an Etalon for even higher resolution observations, which we will need to resolve the water and HD lines in protoplanetary disks and learn about the distribution of water in these disks. The Far-Infrared Imager Polarimeter, FIP, has a wide field of view and allows extremely fast image mapping and polarimetry at 50 and 250 microns. Finally, the Mid-Infrared Spectrometer Camera Transit MIST-T instrument is ultra-stable and ideal for transit planet spectroscopy with a precision of 5 parts per million. We studied a heterodyne instrument that would offer even higher spectral resolving power than OSS, but decided not to include it in the baseline Origins mission concept. That instrument, as well as upscopes to OSS, FIP, and MIST-T, are still possible. Origins has an architecture much like the Spitzer Space Telescope. You can see a little picture of Spitzer down here, drawn approximately to scale. But Origins is scaled up to the size of the James Webb Space Telescope, with 25 square meters of collecting area. And Origins is cooled to 4.5 Kelvin to enable its unprecedented sensitivity. These design features, along with new detector technology, translate into high reward at a low risk, but they do depend on the development of new launch vehicles, such as NASA's Space Launch System, which is motivated by human exploration goals. Origins can map the sky or track solar system objects at up to 60 arcseconds per second, complementing other astronomical survey missions, both ground and space-based. And Origins has a minimum lifetime of 5 years and will carry enough propellant for 10 years. It will be serviceable at 10 years, enabling an even longer mission lifetime. Except in particular spectral windows, our atmosphere is essentially opaque in the far infrared, so we have to go to space to observe the universe at these wavelengths. The far infrared is information-rich, carrying the spectral diagnostics I mentioned earlier. It's also important for the telescope to be cold. To reach the sensitivity levels needed to make our scientific measurements, Origins has to provide astronomical background limited sensitivity. The astronomical background has three main components: zodiacal emission, thermal emission from galactic cirrus clouds, and the cosmic microwave background. Thermal emission from a telescope warmer than about 4 Kelvin would dominate the natural astronomical background, as this series of curves shows. The premier far-infrared telescope to date, Herschel, operated at close to 80 Kelvin. JWST will also be well above 4 Kelvin and will reach the astronomical background limit only at wavelengths shorter than about 15 microns. JW also continues out to about 28 microns. We need a far-infrared telescope that operates at the astronomical background limit down here. The Origins telescope and all of its optical components will be cooled to 4.5 Kelvin or below, and Origins will use next-generation far-infrared detectors to provide 1,000 times better sensitivity than any other far-infrared telescope. In essence, we'll be able to see the universe with new eyes. Even a small cryogenic telescope can be very sensitive, but Origins also has to be large enough to measure the spectra of exoplanets and to measure spectral lines from extremely distant galaxies. In other words, you need enough light collecting power. The exoplanet measurements are possible only with a telescope larger than 5.3 meters, over here, in diameter, and the extragalactic science also erodes if the telescope is smaller than 5 meters. To allow some margin over the science-driven requirements, the margin area up here, while still fitting into a large launch vehicle without having to unfold the telescope, we set the diameter of the Origins telescope to 5.9 meters. It's this line here. Whenever feasible, NASA tests its missions as they fly. In other words, we subject them to the environmental conditions they will experience during launch and operation. That is a great challenge for a cryogenic mission. The JWST telescope was tested at cryogenic temperatures in NASA Johnson Space Center's Chamber A, but the fully integrated observatory with sun shields could not be tested together in flight-like conditions because of the enormous size of the sun shield. You may have heard it's about the size of a tennis court. With its Spitzer-like architecture, however, Origins is more compact. The telescope, as well as its deployable sun shield, can be tested in Chamber A. This will be an important risk reduction measure. Furthermore, the Origins architecture is modular, allowing parallel integration and testing of the flight instruments. And finally, the cryocoolers that cool the Origins telescope will enable faster cool down during testing. These factors reduce the integration and test time and save cost. The enabling technologies for Origins are detectors and cryocoolers. Multiple options exist in each case, and our plan is to develop competing technologies in parallel up to a certain point, and then down select to a particular technology. In the far infrared, we need extremely sensitive detectors in arrays of the order of 10,000 pixels. In the mid-infrared, we need extraordinary stability. Several companies are capable of manufacturing 4.5 Kelvin cryocoolers. In fact, coolers that nearly meet the Origins requirements will fly on JWST and have already flown on Hitomi. And NASA is currently investing in sub-Kelvin coolers to cool the far-infrared detectors. Here you can see that successful operation of the Origin Space Telescope depends on 4 straightforward deployments: a solar array, a communication antenna, a telescope cover, and coming up in a moment, the 2-layer sun shield, which opens like a pop-up tent. Among the many details I presented, what I'd most like you to remember about the Origin Space Telescope is that it was designed to answer 3 compelling science questions and will do much more than that. To achieve its objectives, Origins will be 3 orders of magnitude more sensitive than any previously flown far-infrared telescope, agile enough to survey large areas of the sky, and its mid-infrared instrument will be stable enough to measure biosignatures in the atmospheres of exoplanets. The Origin study team made its recommendations to the US Decadal Survey last August, in August 2019, and we're looking forward to hearing the Decadal Survey's priorities when the report is released next spring. Thank you, and I'll be very happy to take any questions you may have.